Welcome to Topic 2, Atomic Models and Structure of the Atom. We will look at the following essential questions. Explain how the scientific method and experiments were applied as atomic theory evolved. Compare and contrast historical models of the atom, including Democritus, Dalton, Thompson, Rutherford, Niels Bohr, and Schrodinger's quantum mechanical models. And finally, construct an argument explaining how scientific observations and new data lead to the revision or rejection of various atomic models. So we are going to talk about 6 topics in this section. Democritus, Dalton, and J.J. Thomson's plum pudding model will be discussed in this video. The story all begins in ancient Greece around 400 BC. At the time, Aristotle was a prominent philosopher and respected by many. He and other philosophers at the time believed that matter is made out of 4 fundamental elements: earth, air, fire, and water. And this was the widely held belief. Then came along Democritus, who thought they were all wrong, and he was cutting things up, different substances, to find the smallest particle of matter. And he found that there was a point where with a knife he couldn't cut things anymore, or he couldn't break something like a rock into teeny pieces, and there was a point where you can't break it anymore. So he called this particle a tomos, the uncuttable particle. If you look back in history, this is the first time somebody found conceptually the smallest particle of matter. So we say he is the first person who came up with the tomos concept. He did not do any experiments, and as he cut particles, he came up with the smallest particle. He said that atomos or atoms was the smallest particle of matter. It was solid, indivisible, you cannot divide it, and it cannot be destroyed, indestructible, or cannot be created. And he said atoms of all matter are identical. Now there is a problem with this. That means there are no elements. All we have is one element. As you know, that is not true. And then he didn't explain the chemical properties of atoms. So these are the 2 issues with his concept. Then we move on to John Dalton, who lived around the 1800s in England. He was a chemist and he did experiments. He modified Democritus's idea further. He also said that atoms are the smallest particle of matter. It's solid, indivisible, cannot be destroyed or created. However, he noticed that there were different elements. And he said different elements have different chemical properties, and they have different masses and sizes. So now our atoms begin to look like that. And he said during chemical reactions, atoms combine or rearrange to form new substances. He also proposed a theory called the law of multiple proportions, and I will explain it in pictures. So if you consider 2 compounds that are made by the same elements, in this case hydrogen denoted by H and oxygen denoted by O, and each compound has 2 hydrogen atoms in each molecule and 1 oxygen atom in water and 2 oxygen atoms combining in hydrogen peroxide. So if you look how we make these molecules, you have 1 oxygen for water and 2 oxygens for hydrogen peroxide, and for both you have 2 hydrogen atoms each. So if you give a gram amount, if you say we use 16 grams of oxygen for water and 2 grams of hydrogen for water, then we have to double this amount, right? For H2O2, it will be 32, and we have the same amount of hydrogen for H2O2. Now if you look at the ratios of the masses of the different element, for water it's going to be 8:1, the most simplified. If you divide 16 by 2, you get 8 and 1. And then here 13 divided by 2 is 16:2. So you have different whole number ratios of masses combining for oxygen and hydrogen, for water, this one and this one. If you get a 8:1 ratio of hydrogen and oxygen, that's always going to be water. If you get 16:1 ratio, it's always going to be H2O2. So Dalton noticed this, and he said when two or more elements form different compounds, the elements combine in different whole number mass ratios to form each compound. Now, later on, many scientists found that this was true, and this theory is now considered a law. So we call it the law of multiple proportions. Let's look at some pictures to see how it works. So, which of these molecules obey the law of multiple proportions? Now, if you're confused, remember, look for different molecules made with the same building blocks or same elements. So, pause and think. Yep, for question 1, it's these two guys. They are both made with the blue atoms and the black atoms. And for question 2, it's A and B. They have the yellow, red and black atoms together. Let's look at another question. Which of the compounds below obey the law of multiple proportions? So it is these two guys. I gave you chemical formulas here. If you draw them, you have carbon and hydrogen here, carbon and hydrogen here, and this one is a 1:4 ratio, and this is a 1:3 ratio. Now these two have, this one has 2 elements and this one has 3 elements, so they don't obey the law of multiple proportions. Okay, so here's a review of Democritus and Dalton, a comparison. The yellow highlighted section is common to both of them. Democritus didn't do experiments, and he said all atoms are identical. That's the opposite of Dalton. He also proposed that elements combine to form new compounds according to the law of multiple proportions. Here I explained it in different words. When 2 or more compounds are formed by the same elements, the mass ratios of elements between each compound is a different whole number ratio. Before I talk about the next atomic model, I need to give you some background information about the electrical charges or attractions or repulsions of subatomic particles. Now, we know today that there are 3 subatomic particles inside the atoms, and they can be divided because of that into smaller particles. And these subatomic particles shown in the middle make up the nucleus, right? You have protons and neutrons as well as the ones in the electron cloud. And these are their charges. I need you to write this down. Each electron is a -1 charge, and each proton is a +1 charge, and each neutron is a 0 charge, as we learned in the introduction earlier. And then the charges, the opposites, electrons and protons, are attracted to each other, and the plus and plus, or minus and minus, which are protons and protons, are repelling each other, as well as electrons and electrons repel each other. This is very similar to magnets. So north and south poles attract, north and north poles repel, south and south poles repel. In the experiment I'm going to show you in the next slide, the scientists used magnets to do a positive and a negative charge, because north and south poles can be used as positive and negative charges. So a little bit of background. At the time, this is mid 1800s, there was a scientist called William Crookes. He developed this thing called the cathode ray tube. It was called the Crookes tube. The cathode ray tube was a modified version of it. So if you look at this figure, it contains basically a glass tube, and inside is a vacuum. There's hardly any air inside, and there is two metal plates. There is a cathode and an anode. Cathode is the negatively charged metal plate, and the anode is the positively charged metal plate. There was a metal piece inside near the cathode, and there was a hole inside it, so that whatever rays that come will be coming through a small hole as a long beam. So when you connect a battery to this device, you end up seeing a big beam, and it comes through this narrow slit as a long beam. This is called the cathode ray. Since these rays go from the cathode to the anode, they are called cathode rays. So here is a picture of an actual cathode ray tube, and here are the two power supply connections. The electrode cathode is here, anode is here, and down here the glass is painted with a fluorescent screen. That's why you can see the cathode beam. J.J. Thomson wanted to play with this device that was made by Crookes and figure out what cathode rays were. That was his experiment. And if you would know that if you knew these old TVs, they had a cathode ray tube inside it, the old TVs. Anyway, moving on, here's J.J. Thomson's experiment. So here's a cathode ray tube. This is how you turn it on, and then you start seeing a beam of light coming out. So what J.J. Thomson did, he wanted to see if these particles that were coming out of this beam had a positive or a negative charge. So he placed a magnet, the different sides of the magnet. Now you can see this magnet is making it bend the other way. This is a repulsion. And now he flipped the magnet and it's attracted. Same charge as the cathode rays, which is why it's repelling. And then he's going to flip it, and now you see there's an attraction. The beam is attracted to the magnet. So when J.J. Thomson used the magnet in two different ways, in two experiments. In one, he put a positive plate on the one side of the magnet. It got attracted. So when he held a positive charge, the beam was attracted to it. And when he put an opposite charge, which is a negative charge, and the beam deflected. From these two experiments, it's clear that whatever this is made out of has to have a negative charge. And there's a third reason why we know it's negative, because these beams are coming from the negative side and moving towards the positive. So they are attracted towards the positive anyway. So they have to be made out of some kind of negatively charged particle. So please write this down. This is an attraction and this is a repulsion. And here are the experimental observations. And on the right side, I have the corresponding conclusions. Cathode rays move from negative to positive inside a cathode ray tube, and then cathode rays bent towards the positively charged plate and were bent away from the negatively charged plate. Both of those are saying cathode rays are negatively charged. And then he tested different metals for the cathodes and the anodes, and he even put different gases down here for the chamber. All of these he still saw cathode rays. So that means cathode rays are particles that are found in all matter that he tested. And whatever these little particles, he decided that they are fundamental particles of atoms and they are coming from inside the atoms. So for the first time now atoms are divisible. Thomson's atomic model is called the plum pudding model, and atoms contain negatively charged electrons. They are randomly scattered like this. He proposed that there is a positive charge because electrons must repel each other, otherwise they will just fly out of the atom. And he said there is an overall positive charge, like a dough that's holding on the chocolate chip cookies, which are the electrons, and electrons are randomly scattered like this. So this model is called the plum pudding model because there is a British dessert called plum pudding which has plums randomly scattered all over the place. If you can imagine a three-dimensional sphere, you'll have electrons in and out coming all over the place, and the dough in this pudding is the positive charge. Now this is Thomson's model. So here is the summary of Thomson's model and the John Dalton model and Democritus's model. Atoms are indivisible in here and they become divisible. We have electrons as a subatomic particle, and all atoms are the same according to Democritus. Both Dalton and Thompson say they are different in different elements and law of multiple proportions apply. And all three say that atoms are the smallest building block of matter and they cannot be destroyed or created, and that they are solid. I will see you in the next video. Thank you.